The fastener industry is a true empire worth over $90 billion annually. And its flagship products? Massive bolts and nuts that hold our entire industrial infrastructure together. They're not just chunks of steel with machined threads, they're the result of a complete process involving metallurgy, high-pressure forging, heat treatment, and incredibly rigorous mechanical testing. One tiny deviation in material quality, shape, or tightening force can render an entire joint unsafe. In this video, we're going inside the production line that creates giant hex bolts and nuts to show how raw steel transforms into the mechanical foundation of the modern world. The production process for heavy-duty bolts and nuts begins with one fundamental stage: cutting raw blanks. Large diameter steel bars rolled from high-strength alloy steel are fed into industrial cutting machines and divided into segments with precisely controlled length and weight. Modern cutting systems use hydraulic shears or powerful industrial saws, producing clean square cuts that don't distort the metal's internal structure. Throughout the cutting operation, coolant is sprayed directly onto the contact zone to reduce temperature, minimize friction, and wash away metal chips. This maintains cutting tool stability and ensures the blank surfaces remain clean and free from thermal damage. Typically, bolt blanks are roughly twice as long as nut blanks, because bolts require additional material to forge the load-bearing shaft and head in a single production run. During one shift, each cutting machine can process thousands of bolt and nut blanks. Each cut takes just a few seconds, yet the allowable tolerance is extremely tight, because the final shape and mechanical strength of the product depend entirely on the initial dimensions of these blanks. After the blanks are cut, the bolts and nuts move to the heating stage, but the way heat is applied to each component isn't quite the same. For nuts, the entire steel blank feeds into a continuous furnace and is uniformly heated to a temperature range of 1900 to 2100 degrees Fahrenheit. Heating the entire body allows the blank to reach a fully plastic and uniform state. So during forging, the metal can flow evenly inside the die and form a solid hexagonal body before the internal hole is drilled and threads are cut. Temperature is tightly controlled to prevent surface burning while ensuring the core remains soft enough for proper forming. Bolts, however, are heated differently. Instead of heating the entire blank, only the head portion of the steel rod passes through an induction heating system. In a matter of seconds, the front end reaches forging temperature and glows bright orange-red, while the shaft behind it stays significantly cooler. This localized heating method concentrates energy exactly where the hex head needs to form, reduces overall energy consumption, and preserves the mechanical structure of the bolt shaft, which is the primary load-bearing section of the fastener. Right after reaching forging temperature, the blanks are transferred directly into the hot forging zone for shaping. For nuts, the entire evenly heated blank is placed inside a closed forging die, where a high-powered hydraulic press forces the metal to flow according to the die's shape, forming a solid hexagonal body. Under this intense compression, the metal densifies, and its crystalline grains reorganize into a tighter structure, making the steel denser and more uniform. Between each press cycle, the forging die is sprayed with a layer of high-temperature coolant and lubricant. This helps control heat, reduce friction, and protect the die surface during continuous operation. For bolts, the forging process focuses on the head section that was induction heated. The blank is positioned so the hot end sits precisely inside the die, and the press applies force, causing the metal to flow outward, forming the hexagonal head. At the same time, the die is also sprayed with the same type of high-temperature lubricant used in nut forging. When the fluid contacts the hot die, it instantly vaporizes and creates a temporary protective film. This prevents metal adhesion and ensures the bolt head forms cleanly, with sharp, clearly defined edges. Right after forging, both the bolts and nuts are dumped straight into large steel containers for natural cooling in the open air. For big components, this cooling stage typically runs anywhere from 30 to 60 minutes, and can take even longer if the steel mass is particularly heavy. This slow cooling method prevents thermal shock, minimizes the risk of microscopic cracking, and keeps both the shape and the internal structure of the metal stable before the parts move on to the next production stages. Once fully cooled, the bolts and nuts are transferred to the surface cleaning stage. At this point, they're typically loaded in bulk into rotating drum cleaners or vibratory tumbling machines. The rotating drum moves slowly and steadily, creating mechanical friction across the entire surface of the bolts and nuts. This process sharpens the hex edges and leaves the metal surface clean, dry, and uniform. In large-scale production lines, each batch can handle anywhere from a few hundred to several thousand parts at once. Tumbling time usually ranges from a few minutes to several dozen minutes, depending on the size of the parts and the level of oxide scale stuck to their surfaces. Once the surface is cleaned, the bolts and nuts move to the identification marking stage. For nuts, markings are stamped directly onto the hexagonal body, while for bolts, markings are placed on the top face of the head. These symbols indicate the strength grade, technical standards, and manufacturer of each part. They function as an official ID card, mandatory for bolts and nuts to be approved for use in industrial structures, heavy machinery, and large-scale construction projects. Once they've achieved their final shape and received their identification markings, bolts and nuts enter one of the most critical stages of the entire process: thread machining. The threading process for bolts typically begins with a light finishing turn on the shank to achieve a precise diameter and a sufficiently smooth surface. On the lathe, the bolt is firmly clamped and rotated at a steady speed, while the cutting tool simply glides over the surface to correct dimensions before threading. After this, the workpiece is transferred to a thread rolling machine, where 2 or 3 thread rolling dies, engraved with the precise thread profile, press against the shank under high pressure. Thread rolling is a cold forming process that doesn't remove material but rather deforms the surface of the shank, creating threads through plastic flow of the metal. This produces stronger threads with improved fatigue resistance compared to threads cut by a cutting tool. For nuts, threads are created through the tapping method. First, a specialized drill bores a vertical hole through the center of the hexagonal body. Then a tap, a rotating cutting tool with external threads, is inserted into the hole. As it advances, the cutting edges of the tap shave material from the hole wall, forming a precise internal thread profile. During the tapping operation, cutting fluid is continuously supplied to cool the cutting edges, lubricate contact surfaces, and flush away metal chips. Once threading is complete, both bolts and nuts move on to final quality control. First up are geometric checks: diameter, thread pitch, thread depth, concentricity, and sharpness of the thread profile. Threads must match standard thread gauges perfectly. Even the tiniest deviation means rejection. Next come mechanical tests, including surface hardness, tensile strength, and torque resistance. Only after passing all these tests do bolts and nuts move to packaging. At this stage, the products are no longer semi-finished parts. They're full-fledged structural components, ready to ship to construction sites, power plants, steel bridges, or drilling rigs, where every bolt and nut will be responsible for holding together massive industrial systems. From raw steel rods through cutting blanks, heating, forging, thread cutting, inspection, and packaging, giant bolts and nuts complete a manufacturing journey that's precise down to the tiniest details. If you find this journey fascinating, hit that like button to support the video, drop a comment to share your thoughts, and subscribe to the channel to keep exploring the production lines that quietly keep our modern world running. In the scorched Arizona desert, among endless sands, lies the most expensive graveyard on the planet. 4,000 aircraft, worth over $35 billion. This isn't a museum and it's not a junkyard. This is where war machines that once ruled the skies come to die. Picture this: an area bigger than 2,000 football fields, and on every square foot, stories of wars, victories, and defeats. Legendary B-52s that bombed Vietnam rest here. F-14S that defended the skies over Iraq stand here. New patients arrive every single day. But what happens to these giants after they touch down for the last time? Some get stripped for parts in a matter of weeks. Others sleep here for decades, waiting for resurrection. And some just get wiped off the face of the earth. Stick around till the end. You'll find out how machines worth millions die and why this place is called America's Boneyard. (1946). World War II had just ended, and America faced a problem nobody had thought about. Tens of thousands of warplanes were suddenly obsolete. B-17Es, B-24Es, fighters, bombers, all worth billions. But the world wasn't at war anymore. Selling them was out of the question. The technology was classified. Keeping them on active bases? Too expensive. So the military found a solution. Davis-Monthan Air Force Base in Arizona, a place where it rains 4 times a year, where humidity is practically zero, and where the temperature kills any corrosion. Hard-packed alkaline soil, natural concrete, no need for hangars or runways. The desert climate turned this place into the perfect graveyard for aircraft. The first 600 planes from the war flew in. They were parked in neat rows, mothballed and forgotten. Nobody imagined that 70 years later, there'd be over 4,000 aircraft sitting here. The 60s, the Cold War is at its peak. America is building bombers capable of delivering nuclear weapons to Moscow. The B-52 Stratofortress. Weight, 83 tons. Wingspan, 184 feet. A machine built to destroy cities. By the 70s, they'd built over 700 of them. But technology changes fast. Missiles appear that fly faster and more accurately. Bombers become obsolete. Where do you put these giants? Davis-Monthan. The base is expanding. Now it's not just a storage yard, it's a whole industry. 365 personnel. Mechanics, engineers, preservation specialists. They take in aircraft, assess their condition, and decide the fate of each plane. Some get preserved for long-term storage. Others get stripped for parts within a month. Still others head to the guillotine, a giant machine that slices the fuselage into pieces. The decision comes down to one thing. Does the military need this model? The 90s. The Cold War is over, and at the airplane graveyard, the largest destruction in aviation history begins. The Strategic Arms Reduction Treaty demands proof. Bombers must be destroyed so Russian satellites can see it from orbit. They position a B-52 on the pad, and a 13-ton guillotine drops onto the fuselage. The crunch of metal echoes for half a mile. In 15 minutes, a machine that cost $100 million becomes chunks of aluminum. Cameras capture everything for the satellites, proof of destruction. Over several years, they cut up 365 B-52s this way. Each aircraft is a story. Vietnam, Operation Desert Storm, dozens of combat missions. But treaties matter more than history. The metal goes to the smelter. One bomber yields about 50 tons of aluminum, enough to make 1,200 bicycles. That's how legends of the sky die. process begins long before the aircraft touches down in Arizona. The military makes the call. This bird is retired. Could be a lot of reasons. Outdated model, maintenance costs through the roof, political decisions, structural wear after thousands of flight hours. The plane makes its final flight. Pilots joke it's the last ride to paradise, though for the machine it's more like a waiting hell. Davis-Monthan Base greets it in the receiving area. First thing, complete inspection. Engineers check every system: engines, avionics, hydraulics, electronics. A detailed report gets compiled. This will determine the aircraft's fate. Category 1. Storage with restoration potential. These birds can return to service in 5, 10, even 15 years. Category 2, an organ donor. Everything valuable gets stripped out. Category 3, my complete disposal. This plane goes under the cutting torch within weeks. Decision made. Preservation begins. If a plane ends up in storage, it's prepped for a long sleep in the desert. This isn't just park it and forget it. It's a meticulous process refined over decades. First, they drain all fluids: fuel, hydraulics, oils, every last drop. Even the slightest residue can cause corrosion or fire. Then they preserve the engines. They're coated with a special compound that protects the metal from oxidation. The cockpit is sealed. Every opening, air intakes, nozzles, hatches, gets covered with special film. It reflects sunlight and keeps the internal temperature from reaching critical levels. Without it, the cockpit turns into an oven. Desert temperatures in summer hit 120 degrees Fahrenheit. Electronics are sealed in protective bags with silica gel, which absorbs moisture. Landing gear gets treated with anti-corrosion coating. The whole process takes about 3 weeks. After that, the plane is rolled out to its spot. Neat rows like a parade of frozen giants. Here it can sit for years. But most aircraft meet a different fate. They become donors. Picture this: hundreds of planes flying overhead that need parts. An engine for an F-16 costs $3 million. Brand new. But what if you pull it from a mothballed airframe? $800,000. The savings are massive. That's why there's an entire disassembly industry here. Mechanics show up with orders. Need a radar? Pull it from tail number 412. Need a turbine? That F-15 over there will give up its own. The process is surgical. Aircraft aren't stripped barbarically. They're disassembled by the book. Every part gets cleaned, inspected, tested. They document serial numbers, flight hours, condition. Then they package it and ship it to warehouses. One retired aircraft can give life to dozens still flying. Every year, more than 20,000 parts ship out from here. The value of those parts? Over $500 million annually. The aircraft boneyard operates like a giant parts store for all of American aviation. But some planes aren't so lucky. Their time is truly up. The model's obsolete and nobody needs their parts. Or treaties demand complete destruction. That's when the final act begins. The aircraft gets rolled onto a special pad. This is where the monster works, the Igor guillotine. 13 tons heavy, tall as a 3-story building. It's a hydraulic cutter that can slice a B-52 fuselage clean in half in 20 seconds. Brutal process, but efficient. The blade drops and metal 3/4 of an inch thick cracks like cardboard. The fuselage splits apart. Then excavators with shears roll in. They cut the wings, rip off the tail, crush the cockpit. In one day, a single crew can turn 5 aircraft into a pile of scrap. Aluminum gets sorted by grade, titanium separate, steel separate. All of it goes to the smelter. One F-14 Tomcat yields about 12 tons of metal, enough to make 40,000 soda cans. Circle of materials. But not every plane stays here forever. Some come back to life. History's seen dozens of cases where an aircraft that slept 10 years in the desert took to the skies again. The most famous example? B-1 Lancers. In 2004, they were pulled from service and mothballed. 5 years later, the military realized they'd made a mistake. These machines were still needed. 18 airframes were brought back online. The restoration process took months. Engineers stripped protective coatings, checked every system, replaced all fluids, tested engines. Cost of restoration? $15 million per airframe? That's 10 times cheaper than building new. These B-1s flew combat missions again. Afghanistan, Syria, Iraq. Machines considered dead were dealing death once more. The Arizona desert proved to be better storage than any hangar. Dry air preserved the metal perfectly. Not a speck of rust after 10 years under open sky. $4,200 aircraft sit at the Boneyard today. That's more than all the aviation museums in the world combined. This collection's worth over $35 billion. Around 300 new birds arrive every year, and roughly the same number leave. Some for parts, some for the smelter, some return to active duty. The base operates year-round, 365 days. No days off. A staff of 400 keeps this giant machinery of death and resurrection running. The economic impact is massive. Annual savings for the U.S. Air Force, over $1 billion. Money they don't have to spend on new parts. Foreign militaries come here like it's a marketplace. They buy whole aircraft for their museums or training. Australia bought 20 retired F-18 Hornets. Israel took several dozen helicopters. The Boneyards become an international hub for trading aviation history. And so, beneath the scorching Arizona sun, ends the life of machines that once embodied power and technology. Each of these aircraft isn't just metal and electronics. These are the stories of pilots who trusted them with their lives. These are missions flown over Vietnam, Iraq, Afghanistan. These are technologies humanity spent decades developing and billions of dollars perfecting. There's no museum romance here. Here's the harsh truth. Every machine is mortal, even those that ruled the sky. But there's a certain justice in this. Aircraft don't rot in junkyards. They donate their organs to brothers still flying. They transform into materials for new technologies. Some resurrect for final combat missions. The aircraft boneyard isn't the end, it's transformation. From the ashes of old machines, new ones are born. And every time a fighter climbs into the sky with an engine stripped from a mothballed bird, somewhere in the desert a metal giant smirks. I'm still flying, just differently. What if I told you there's a metal that can't be destroyed by fire, pressure, or time? A material without which aviation would grind to a halt, lights would go dark, and rocket engines would fall silent. And here's the thing. It's so rare that the entire world is competing for every single gram. Tungsten has the highest melting point of any metal on Earth. A staggering 6,192 degrees Fahrenheit. That's a temperature at which most other metals would have long since turned to vapor. Annual global tungsten production ranges from 85 to 100,000 tons per year. But here's what's striking. Up to 40% of all tungsten consumed worldwide comes from recycled material. That's a massive number, showing just how valuable it is. Total global tungsten reserves are estimated at roughly 3 to 3.5 million tons, nowhere near the reserves of iron or aluminum. But here's what really matters. By the end of this video, you'll learn a secret about tungsten that the industry hides and almost nobody talks about. Something that will flip your understanding of the metal holding civilization together. Picture a massive underground mine somewhere in Vietnam, China, Russia, or Canada, the world's biggest tungsten producers. Deep in the Earth's belly, hundreds of feet down, lie ores containing tungsten. Not pure metal, but complex minerals, wolframite and scheelite. Wolframite is a compound of iron, manganese, and tungsten. Scheelite is calcium tungstate. Geologists use various methods to identify and assess tungsten ore deposits. Then, using powerful drilling rigs and explosives, the ore is extracted from deep underground. It's tough, dangerous work, requiring high-tech equipment and strict safety standards. Thousands of tons of ore get hauled to the surface daily by massive underground trucks. Powerful blasts shatter the rock, exposing the valuable ore. It's like a controlled earthquake in miniature. After the blast, the ore gets loaded into haul trucks with capacities up to 300 tons and transported to the processing plant. After extraction, the ore goes to a processing plant. Here it undergoes several stages to separate valuable wolframite or scheelite from other rocks. First, the ore is crushed in crushers and mills into a fine powder. Massive jaw crushers with deafening roars break down car-sized chunks into fist-sized pieces. Then the crushed ore enters ball mills, giant rotating drums filled with steel balls. In these mills, the ore is ground into an extremely fine powder, almost like flour. Next, various enrichment methods are applied, such as gravity separation, magnetic separation, and flotation. Gravity separation uses the difference in density. Tungsten minerals are heavier than waste rock. Magnetic separation separates weakly magnetic wolframite particles from non-magnetic impurities. Flotation is a process where the ground or powder is mixed with water and special chemical reagents in large tanks. These reagents selectively attach to tungsten mineral particles, making them water repellent. Air is then pumped through the mixture, creating millions of tiny bubbles. The tungsten mineral particles latch onto these bubbles and rise to the surface, forming a foam. Other unwanted minerals stay at the bottom. This enriched foam is collected. These processes yield a concentrate containing 60 to 70% tungsten trioxide, which is an intermediate form. The resulting concentrate is then processed at metallurgical plants to obtain pure tungsten. This is a complex chemical process that can involve alkaline leaching, precipitation of ammonium paratungstate, and its subsequent calcination to produce tungsten oxide. The concentrate is dissolved in alkaline solutions at high temperatures. Ammonium paratungstate, an intermediate compound, is then precipitated from the solution. This compound is calcined at temperatures around 1100 to 1500 degrees Fahrenheit, producing tungsten oxide, a yellow powder. Tungsten oxide is then reduced to metallic tungsten by heating it in a hydrogen atmosphere at temperatures ranging from 2000 to 3300 degrees Fahrenheit. Inside specialized furnaces, tungsten oxide is heated in a stream of hydrogen. The hydrogen strips away oxygen from the tungsten oxide, releasing pure metallic tungsten. The result is a fine gray tungsten powder, the foundation for every product that follows. It's from this powder that tungsten rods, bars, and other blanks are formed through sintering. The tungsten powder is pressed under high pressure into the desired shape, then sintered at extremely high temperatures in a hydrogen atmosphere. This allows the powder particles to bond together, forming a dense, durable material. Sintering temperatures can reach 5,400 degrees Fahrenheit. At that temperature, the powder particles begin to fuse, creating a monolithic structure. The process takes place in furnaces with controlled atmospheres to prevent oxidation. One of the most critical applications is the production of hard alloys known as tungsten carbides. These alloys, combining tungsten with carbon, plus cobalt or nickel as a binding agent, rank among the hardest man-made materials. Tungsten carbide is created by heating tungsten powder with carbon at temperatures around 2,500 to 2,900 degrees Fahrenheit. Tungsten carbide crystals form, which are then ground into powder. This powder is mixed with cobalt or nickel, serving as a binder, pressed into molds, and sintered. Tungsten carbides are used to manufacture cutting tools, drill bits, milling cutters, lathe tools that can machine the hardest metals and alloys. Without tungsten carbides, modern mechanical engineering, metalworking, and oil and gas extraction would be impossible. 2 pounds of tungsten can become a drill bit capable of boring thousands of feet through rock, demonstrating its incredible efficiency. Tungsten is also widely used in the military industry for manufacturing armor-piercing shells and bullet cores. Thanks to its high density and hardness, tungsten alloys have excellent penetration characteristics, providing high effectiveness against armor. It's also used in heavy armor plating and counterweights. In electronics and electrical engineering, tungsten is irreplaceable. It's used to produce filaments in incandescent bulbs, welding electrodes, electrical contacts, and other components requiring high heat resistance and electrical conductivity. Because of its high melting point, it's used in the space industry for components subjected to extreme temperatures. High-temperature alloys containing tungsten are used in aircraft engines, turbines, and other devices operating under conditions of extreme heat. Alloying with tungsten increases the heat resistance of other metals. In medicine, tungsten is used in manufacturing X-ray tubes thanks to its high atomic number, which effectively blocks X-rays. It's also used in radiation shielding, similar to lead, but with lower toxicity. Plus, tungsten is used to create ballasts and counterweights in race cars, aircraft, and yachts thanks to its high density. It's also a component in certain jewelry pieces because of its hardness and scratch resistance. Tungsten is one of the least abundant elements in Earth's crust, which makes its mining and production especially valuable. Global tungsten reserves that are economically viable to mine are estimated at roughly 3 to 3.5 million tons. However, when you factor in potential but not yet explored resources, the total volume could be significantly higher. This is, of course, incomparably less than reserves of metals like iron or aluminum, which underscores its strategic value. Annual global tungsten production, measured in tons of pure metal or tungsten oxide equivalent, fluctuates, but in recent years it's been approximately 85 to 100,000 metric tons per year. This figure includes both primary extraction from ores and recycling, which is becoming increasingly important. Imagine being able to take a worn-out tool that's already served its purpose and turn it back into something new, without spending energy and resources mining ore from scratch. That's exactly what happens with tungsten. Tungsten recycling is among the most advanced and efficient of all metals. By various estimates, up to 40% of all tungsten consumed worldwide comes from recycled material. That's a massive number, demonstrating its value and economic viability. Where does used tungsten come from? The main source of secondary tungsten material is, of course, spent cemented carbides. Those cutting tools, drill bits, and milling cutters made from tungsten carbide. After intensive use, they wear down, lose their edge, or break. Instead of tossing them in a landfill, they're collected and sent to recycling plants. Other sources include tungsten-containing scrap metal, leftovers from tungsten product manufacturing, plus certain electrical contacts and wires. Recycled tungsten is significantly cheaper to produce than primary metal because it eliminates the expensive and energy-intensive stages of ore mining and initial processing. Recycling dramatically reduces tungsten production's environmental footprint. It minimizes the need for mining operations, cuts energy consumption, reduces industrial waste, and lowers greenhouse gas emissions. This makes production greener and more responsible. And so, after a journey from underground blast through grinding into powder, and through flotation with millions of bubbles, through chemical dissolution and reduction in a hydrogen atmosphere at 1800 degrees, through sintering at 3000 degrees, a metal is born with the highest melting point on Earth, capable of withstanding 6192 degrees Fahrenheit, a metal without which modern industry, aviation, aerospace, and medicine would be impossible. And the most remarkable part, nearly half of this metal is born anew from old tools, making tungsten one of the most environmentally friendly strategic materials of our civilization. Picture this. Glass that once shattered into deadly shards now saves lives. How did humanity transform a fragile substance into armor for your car? Every year, the world produces over 100 million square meters of automotive glass, enough to cover an entire country. But the real magic happens where molten rock becomes a perfectly smooth surface, in furnaces reaching temperatures over 2700 degrees Fahrenheit. That's hotter than the surface of molten lava. How did ordinary quartz sand become the foundation of a safety technology we can't imagine modern transportation without? What accidental experiment changed the history of automobiles forever? You'll discover how the first safety glass was created, what secrets hide within its layers, and why modern windshields can withstand the impact of a rock at 60 miles per hour. Watch until the end. The finale reveals how many stages glass goes through to protect your life. The history of automotive glass production is closely tied to the development of the automobile industry, which emerged in the late 19th century. When the first cars began appearing on roads, they weren't equipped with glass at all. The open body design only partially protected passengers, while dust, wind, insects, and other hazards made trips extremely uncomfortable. Later, as cars got faster, the need arose to install protection for drivers and passengers. Windshields started being made from ordinary window glass, which, while providing some protection, had a serious flaw. During accidents, it shattered into large, sharp shards, leading to numerous injuries and deaths. Glass sliced faces, necks, arms of drivers and passengers. This was a real problem demanding an urgent solution. The first revolutionary breakthrough in automotive glass came with the creation of laminated glass. And it happened by accident. In 1903, French chemist Edouard Benedictus accidentally knocked over a flask coated with nitrocellulose. The glass cracked, but stayed intact thanks to a thin plastic layer. This accident inspired the scientists to create multi-layer glass, which later became the foundation for laminated safety glass. By the 1910s, laminated glass started appearing in premium automobiles. Its construction consisted of two glass layers with a thin, transparent film sandwiched between them. On impact, the glass wouldn't shatter. Cracks would stay trapped in the film. In the 1920s, laminated glass became widely used in windshield production. Its main advantage? Enhanced safety. Even in serious crashes, fragments wouldn't fly everywhere. They'd stay locked in the polymer layer. The next stage in automotive glass development came in the 30s, when tempered glass manufacturing technology was patented. This material was produced by heating glass to high temperatures followed by rapid cooling. As a result of this process, the glass became stronger, and when it shattered, it broke into small pieces with blunt edges, minimizing injuries. In the mid-20th century, tempered glass began to be used for side and rear car windows. It was cheaper to produce compared to laminated glass and provided a sufficient level of safety for these parts of the vehicle. In the 50s and 60s, automotive glass became even more advanced thanks to technological developments. Important changes occurred. Improvements to laminated glass and the development of new polymer films made laminated glass more transparent, resistant to ultraviolet radiation, and durable. Mass production and automation of manufacturing processes allowed for a reduction in the cost of automotive glass. One of the biggest technological breakthroughs in glassmaking came in 1959 with the invention of the float process. This technology, developed by British company Pilkington, made it possible to manufacture perfectly smooth glass by spreading molten glass across a surface of molten tin. Picture this. Red-hot liquid glass pours onto a mirror-like surface of molten metal and spreads itself out, forming a perfectly flat sheet. Thanks to this method, glass became more uniform, stronger, and accessible for mass production. The float process is still the foundation of automotive glass manufacturing today, ensuring precise dimensions, smooth surfaces, and high quality. In the second half of the 20th century, automotive glass underwent even more changes aimed at improving safety and comfort. In the 60s, heating wires started being installed in rear windows to prevent fogging and freezing. In the 80s, glass with special metallic coatings appeared that reflected sunlight and reduced cabin heating. UV protective glass, thanks to new technologies, began providing nearly complete protection from harmful radiation. Modern automotive glass is divided into several types depending on its purpose and manufacturing technology. The windshield is typically laminated glass consisting of two layers of glass with a polymer film sandwiched between them. This design ensures that when damaged, the glass doesn't shatter into sharp fragments. Side and rear glass are most often tempered glass, which breaks into small blunt pieces upon impact, reducing injury risk. Panoramic roofs or other specialty glass types often use laminated or tempered glass with special coatings for ultraviolet radiation protection. The main components of glass are natural materials mixed in specific proportions to achieve the desired properties. Quartz sand is the primary ingredient of glass, providing its transparency. It must be extremely pure with minimal impurities. Soda is added to lower the melting point of glass. Lime improves the mechanical strength and chemical properties of glass. Additional additives are used to adjust color, transparency, resistance to ultraviolet light, and other characteristics. The raw materials are purified, dried, and ground to a uniform consistency. It's critical that impurities that could affect glass quality are eliminated as much as possible. After the raw materials are prepared, they're loaded into specialized furnaces for melting. The melting temperature to form glass reaches around 5,000 degrees Fahrenheit. This is the temperature at which stone transforms into liquid. During the melting process, the raw materials become a uniform, viscous fluid. The glass mixture gets stirred to distribute components evenly. This matters. You want to avoid air bubbles or inconsistencies in the finished product. Glass melting furnaces come equipped with modern temperature control systems and process automation, ensuring top quality end results. After melting, the glass mass undergoes forming, which in modern production is most often done using the float process. Liquid glass flows out of the furnace and enters a bath of molten tin. Thanks to tin's high density, the glass mass spreads evenly across its surface. Under its own weight, the glass forms a perfectly flat and smooth surface. Gradually lowering the temperature, the glass hardens. By the time it exits the bath, it's ready for processing. The float method allows manufacturers to produce glass sheets with precise geometric parameters and high surface quality. After cooling, the glass sheets are cut according to the dimensions needed for automotive production. Automated cutting machines ensure precision in the process. To prevent cracks and chips, the glass edges are ground down. Each sheet undergoes inspection for defects like microcracks, bubbles, or other damage. To guarantee the strength and safety of automotive glass, it goes through a tempering process. The glass is heated to around 1,112 degrees Fahrenheit. Then the glass surface is rapidly cooled by air jets, while the inner layers cool more slowly. This creates tension that increases impact resistance. When tempered glass breaks, it shatters into small, safe fragments, minimizing the risk of injury. Windshields use laminated glass, a construction of glass and polymer film. Its manufacturing involves several steps. A polymer film is placed between two glass sheets. The construction is put into a vacuum press to eliminate air bubbles. Next, the glass is heated in an autoclave to 284 degrees Fahrenheit under high pressure. This creates a rock-solid bond between the layers. Laminated glass has exceptional impact resistance, and when damaged, it stays held together by the polymer film, keeping drivers and passengers safe. To enhance automotive glass properties, various coatings are applied. Anti-glare coatings reduce reflections from the sun or headlights of other cars. UV protection, special layers block harmful ultraviolet radiation. Hydrophobic coatings make water sheet right off the glass surface. Heating elements, thin heating wires can be embedded in the windshield, making it easier to clear ice or fog. To achieve the exact shape needed, special thermoforming equipment is used. The glass is heated to a temperature where it becomes pliable and is formed according to the specified parameters. In the final stage, every piece undergoes rigorous inspection. They check for clarity and defects. The glass is tested for impact resistance and load endurance. Standards compliance, dimensional accuracy, shape, and other parameters are verified. The finished automotive glass is packaged to prevent damage during transport. It's shipped to auto plants or service centers where it's installed in vehicles. And that's how, journeying from quartz sand through the hellish flames of furnaces at 5,000 degrees Fahrenheit, through a bath of molten tin, through tempering and lamination, glass is born, capable of protecting life at 75 miles per hour. This is the story of how an accidentally shattered flask changed the automotive world forever. Automotive glass production is a high-tech process combining physics, chemistry, and engineering. Thanks to modern technology and strict quality control standards, automotive glass delivers safety, comfort, and durability. Every time you get in a car, remember, between you and danger, a thin layer of glass that's passed through dozens of production stages to save your life in that critical moment.
Picture this: 8% of all CO2 on the planet comes from one industry, steel. Every single second, the world produces 60 tons of steel, and every ton leaves behind nearly 2 tons of carbon dioxide. But in Sweden, something seemingly impossible happened. They made steel without coal, zero coal. Instead, hydrogen and electricity. Sounds like science fiction? In 2021, a Volvo truck built from this steel hit the roads. The first vehicle in history made from steel with a zero carbon footprint. How is humanity walking away from a technology that's 3,000 years old? You'll learn why traditional steelmaking is killing the planet how hydrogen is replacing coal and blast furnaces, and why this revolution will change everything, from skyscrapers to cars. Watch to the end. The finale will show you that the future of steel isn't black anymore. It's green. The history of steel production began 3,000 years ago when humanity learned to smelt iron. The principle remained unchanged for millennia. Iron ore is heated with coal. Carbon strips oxygen from iron oxide, and you get pure iron. This is called reduction. And the byproduct? Carbon dioxide, which escapes into the atmosphere. For centuries, nobody cared. In the 19th century, blast furnaces appeared, steel giants as tall as a 20-story building. Inside, temperatures hit 3,600 degrees Fahrenheit. Superheated air blasts in from below, while iron ore and coke, specially fired coal, get loaded from above. The ore descends, meets the carbon, and out comes molten pig iron, glowing orange like lava. Pig iron then becomes steel by blowing oxygen through it to remove excess carbon. This technology fueled the Industrial Revolution, built skyscrapers, bridges, ships, automobiles, but it comes with a monstrous cost. Every ton of steel requires about 1,300 pounds of coke. When burned and used to reduce the ore, it produces nearly 4,000 pounds of carbon dioxide for every ton of steel. Global steel production, almost 2 billion tons per year. Do the math, around 7.5 billion tons of CO2 annually. That's 8% of all global greenhouse gas emissions, more than all aviation worldwide. If the steel industry were a country, it would rank third in emissions after China and the US. And the problem's getting worse. Demand for steel is rising, especially in developing countries. By 2050, emissions from steelmaking could double if nothing changes. Humanity's caught in a trap. Modern civilization is impossible without steel, but steel is killing the climate. Aluminum or plastic can't replace steel in most applications. The properties are just too different. We needed a revolution. And it started in cold Sweden, in the city of Luleå, above the Arctic Circle. In 2016, 3 Swedish companies, SSAB, Vattenfall, and LKAB, announced the launch of the Hybrid project, Hydrogen Breakthrough Iron-Making Technology, a breakthrough technology for producing iron with hydrogen. The idea seemed insane. Replace carbon with hydrogen in the ore reduction process. Instead of the iron plus carbon reaction that produces CO2, use iron plus hydrogen, which gives you H2O, water, just water, no carbon dioxide. But the challenge was titanic. They needed to build a hydrogen production plant using electrolysis, powered by renewable energy. They needed to design direct reduction reactors that use hydrogen to process iron. They needed to prove this iron could be transformed into quality steel and make all of it economically viable. 5 years of work, hundreds of millions of euros in investment. In June 2021, they fired up the world's first hydrogen-based steel plant in Luleå, a pilot facility, but fully operational. The revolution had begun. Now let's break down how this actually works. The process starts with hydrogen production. Typically, hydrogen comes from natural gas, but that creates CO2 emissions. Hybrid uses water electrolysis. They run electric current from wind and hydroelectric plants through water. The water splits into hydrogen and oxygen. Pure green hydrogen, zero emissions. This hydrogen feeds into a shaft furnace, a direct reduction reactor. Iron ore pellets get loaded from the top. These are walnut-sized granules made of iron oxide. Superheated hydrogen enters from below at around 1,500 degrees Fahrenheit. The hydrogen rises up through the pellet bed. A chemical reaction occurs. Hydrogen strips the oxygen from the iron oxide. What forms is metallic iron and water vapor. Yep, just steam. The pellets sink downward, gradually losing oxygen and transforming into porous iron, called sponge iron or direct reduced iron, DRI. What comes out are gray, porous granules of pure iron.
But this isn't steel yet. The sponge iron gets loaded into an electric arc furnace, a massive steel vessel with graphite electrodes as thick as telephone poles. They run monstrous electrical current through these electrodes, tens of thousands of amps. Between the electrodes and the metal, an electric arc forms with temperatures reaching 6,300 degrees Fahrenheit. That's hotter than the surface of the sun. The iron melts in minutes. They add alloying elements, chromium, nickel, molybdenum, to get the exact grade of steel they need. The electricity for the furnace also comes from renewables, hydroelectric plants, and wind turbines. The molten steel glows blindingly white. They pour it into molds, let it cool. What you get are steel ingots or billets, indistinguishable in properties from conventional steel, but their carbon footprint, practically zero. The entire process uses not a single ounce of coal, not a single ounce of coke, not a cubic foot of natural gas, just iron ore, hydrogen, electricity, and water. This is fossil zero metallurgy. In August 2021, a historic event occurred. The company SSAB shipped its first batch of green steel to a customer. The buyer was Volvo. This steel was used to manufacture body parts for trucks, the first vehicles in human history made from carbon-free steel. Volvo ran tests: strength, fatigue resistance, weldability, corrosion resistance, all parameters identical to regular steel, or even better. Because the process is more controlled, fewer impurities. In 2022, other companies also received batches of green steel, manufacturers of excavators, construction equipment, household appliances. Mercedes-Benz ordered a batch for use in passenger cars. SSAB announced that by 2026, it will launch the first full-scale hydrogen-based plant. Capacity, 1,300,000 tons of steel per year. By 2035, all SSAB products will be carbon-free. The company promises to cut Sweden's emissions by 7% just by switching to hydrogen. But hybrid isn't the only project out there. Right there in Sweden, they're building the H2 green steel plant, 5 million tons per year. Launch is set for 2025. In Germany, ThyssenKrupp is converting its blast furnaces to hydrogen. Austria's voestalpine fired up a pilot hydrogen plant. South Korea's POSCO is pouring billions into the technology. Even China, the world's biggest steel producer, announced it's building hydrogen plants. Governments are backing the tech with subsidies and tax breaks. The European Union rolled out a carbon tax on steel imports. More emissions, higher tariff. That makes green steel competitive. The big problem right now? The cost of green hydrogen. Hydrogen from electrolysis is still pricier than hydrogen from natural gas, but prices are dropping. Over the last 10 years, the cost of electrolysis fell by 2/3. As renewable energy capacity grows, hydrogen will get cheaper still. Another advantage of hydrogen metallurgy? It's way more compact. A traditional steel plant is an absolute monster of a complex. Coking plants, sintering factories, blast furnaces, converters, rolling mills, all of that eats up miles of land. A hydrogen facility is much tighter. An electrolyzer to produce hydrogen, a shaft furnace to reduce the ore, an electric arc furnace for melting. You can build a plant right next to your iron ore source and renewable energy, instead of hauling raw materials halfway across the globe. Swedish projects use ore from local Kiruna deposits, one of the largest in the world, and electricity from hydroelectric plants and wind farms in northern Sweden. Logistics get simpler, costs drop. Steel quality can be higher too. Direct reduction with hydrogen gives you purer iron, with less sulfur, phosphorus, and other nasty impurities. That steel's better suited for high-strength applications: aviation, cars, bridges, wind turbines. Ironically, the green technology turns out to be technically superior as well. Sure, there are challenges. Hydrogen metallurgy demands massive amounts of electricity. Producing 1 ton of steel requires about 3.5 megawatt-hours of power. That's a small city's daily energy consumption. That's why projects are being built where cheap renewable energy is abundant. Scandinavia with its hydroelectric plants, Germany and Denmark with wind, Australia with sun. You also need infrastructure for storing and transporting hydrogen. It's an explosive gas. They're building special pipelines, storage tanks, safety systems. But all of this is solvable. The technology exists, the economics are starting to add up, and so is the political will. Analysts predict that by 2030, 10% of the world's steel will be produced with hydrogen. By 2050, a third or even half. That'll cut CO2 emissions by 1 billion tons annually, like removing 200 million cars from the roads. The metallurgy revolution, quiet but powerful.
And just like that, journeying from ancient blast furnaces where iron was smelted with coal 3,000 years ago, through recognizing an environmental catastrophe and searching for solutions, humanity arrived at hydrogen, the most abundant element in the universe. The very same gas that stars are made of now melts steel on Earth. Instead of black smoke from blast furnace stocks, water vapor. Instead of billions of tons of carbon dioxide, water. This is a story about how a technology that seemed unshakable was rewritten in a decade. Every time you see a new skyscraper, bridge, or car 10 years from now, know this: inside, possibly, green steel. Metal produced without harming the climate. The metal of the future, made from ore, water, wind, and sun. Black metallurgy is turning green. And this isn't just a color change, it's a paradigm shift. Humanity has proven you can build civilization without destroying the planet, even in an industry as dirty as steel. The hydrogen revolution has begun, and it will change everything.